Limitations of algorithm power. Under this, we talk about lower bound arguments, decision trees, PNP, NP-hard, and NP-complete problems. First and foremost, let's see what is a lower bound. Consider a type of problem you need to solve. Lower bounds are estimates on a minimum amount of work needed to solve a particular type of problem. We need to establish a limit on the efficiency of the algorithm. Say if L of n is the lower bound of an algorithm, then it is not possible to find any other algorithm whose time complexity is less than L of n. L of n is the limit, it is the least amount of work needed to solve that particular type of problem. Next, lower bound arguments. If you have to compare the two algorithms, selection sort and Tower of Hanoi, selection sort is considered as a reasonably fast algorithm since it has quadratic efficiency. Whereas Tower of Hanoi is very slow because it has exponential efficiency. But think about it, these two algorithms are solving different kinds of problem. So the fairer approach is to ask how efficient an algorithm is with respect to other algorithms of the same category of problems. For example, here we have to consider selection sort and any other sorting algorithms. So then you realize that selection sort is slower compared to other sorting algorithms. And Tower of Hanoi is the fastest possible algorithm for the kind of problem it solves. While analyzing the efficiency of an algorithm with respect to other algorithms of the same category of problems, one should know the best possible efficiency of any algorithm for that particular problem. Knowing that lower bound helps in improving the solution. Trivial lower bounds. One of the simplest ways to find out a lower bound class is by counting the number of inputs that must be processed and the number of outputs that must be produced. The algorithms must at least read and write these values. Such a count gives a trivial lower bound. For example, to find out all the permutations of n distinct items, lower bound, that is omega, is n factorial. Because the size of output is n factorial and it is a tight bound because any good algorithm will spend a constant time on each of these values. Next, information theoretic arguments. In this approach, we seek to establish a lower bound based on the amount of information an algorithm has to produce. For example, if you have to find out the exact number selected from 1 to n only by asking yes or no question, the amount of uncertainty of any algorithm here is log base to n. It is the number of bits needed to specify a particular number among the n possibilities. Each yes or no question will yield at most one bit. So any algorithm to solve this particular problem will need at least log base to n steps in worst case. Adversary arguments. In the previous problem, assume that there is a hostile adversary who makes the algorithm ask as many questions as possible. Starts by considering that each of the number between 1 to n is a potentially selected number. After each question, adversary gives an answer, leaving her with a larger set of number consistent with this and all the previous answers. This strategy leaves her with at least one half of the numbers she had before her last answer. At least log base to n questions need to be asked by any algorithm in the worst case. Problem reduction. The idea of reduction can be used to find out a lower bound to show that problem P is at least as hard as another problem Q with a known lower bound, we need to reduce Q to P. We know the lower bound for Q and we are assuming that the difficulty levels are same. So we reduce problem Q to P. We should know that an arbitrary instance of problem Q can be transformed to an instance of problem P. So any algorithm solving P would solve Q as well. Then a lower bound for Q will be the lower bound for P. The next topic under limitations of algorithm power is decision trees. Some of the important algorithms like sorting and searching involves comparing of their inputs. In these scenarios, we can use decision trees. This is an example for decision tree for finding the minimum of three numbers. First condition is if A is less than B. Based on that outcome, we continue to go left or right. If A is lesser, we continue to the left side, otherwise to the right side. Number of comparisons in the worst case is equal to the height of the algorithm's decision tree. The next topic under limitations of algorithm power is about PNP, NP-hard and NP-complete problems. This is an important topic. I have tried to simplify it as much as possible. Let's start with a broader view. P, NP, NP-hard and NP-complete, all these are class of problems. For deterministic algorithms, we know the exact working of algorithm. For non-deterministic algorithm, we are not aware of one or more steps of the algorithm. We cannot determine it. Firstly, we have P. P is the simplest class of problems. P stands for polynomial time. These are deterministic algorithms that can be solved in polynomial time. Examples are basic mathematical algorithms, string operations, sorting, shortest path algorithm, linear and binary search algorithms. These are considered to be very easy. Next we have NP. N in NP stands for non-deterministic. P is for polynomial time. So this class NP contains non-deterministic algorithms that can be solved in polynomial time. For example, integer factorization, graph isomorphism. Because of the non-deterministic property, these are considered to be medium hard. Next, let's jump to NP hard, then we come back to NP complete. So what is NP hard? If a problem does not have any known polynomial time algorithms and it is non-deterministic in nature, then it is considered to be NP-hard. Examples are k-means clustering, traveling salesman, graph coloring. Since it is non-deterministic and we don't know any polynomial time algorithm for it, it is considered to be the hardest problems of computer science. Basically, NP-hard problems do not have any kind of solution at the moment. But when you consider an NP-hard problem and later on find an algorithm which is non-deterministic, then it becomes NP-complete. So NP-complete is an NP-hard problem for which you or someone else have derived a non-deterministic algorithm. Initially it was NP-hard, but later on it moved to NP-complete. We can see this clearly in the Venn diagram I'll show next. So the examples for NP-complete problems are traveling salesman, graph coloring. It is a hard class of problems. This is a Venn diagram representing all the problem classes we just discussed. If a problem has a deterministic and polynomial time algorithm, it goes here. If a problem can be solved in polynomial time but it is non-deterministic in nature, then it goes to the class NP. As I mentioned, these are non-deterministic algorithms, but as and when they get converted to deterministic, they get added to the class P because they just became deterministic and they can be solved in polynomial time, they go to P. That was about the polynomial time. Next, there are some problems which cannot be solved in polynomial time, at least at the moment. We don't know how to solve it in polynomial time. And it is non-deterministic in nature. So we put it in NP hard because it's very hard to find out an algorithm that can be solved in polynomial time. So that particular problem goes to this class. By the method of reduction, if you are able to find or create an algorithm to solve this NP hard problem, then it becomes NP complete. Now, why this overlapping area for NP complete? Because the problems that come under this class were once NP hard problems. We did not know how to solve them. They were the hardest ones. But eventually, after a lot of research and after a lot of work, we found a non-deterministic algorithm for it. That's why it is intersecting between NP circle and a NP hard circle. These concepts are very complex, but I hope this broader explanation gave you some insight.